So we're on to our second, third, and hopefully our fourth question in this video, if I can make it through in 15 minutes. This one says, why we don't really need the basic exponential growth formula. So we're going to write a function to model each of these situations using the formula at the top of the column. So we see we have our basic formula here and our compounded periodically formula here. The first one says Sarah places $1,200 in a bank account that gives 4% interest per year. Write a function to model this situation. So here we know our p-value is 1,200. 1 plus r is going to be 1.04 because we're increasing by 4%. 0.04 is 4%, and then to the time. In the next one, Sarah places $1,200 in a bank account that gives 4% interest compounded once per year. Write a function to model this situation. So the only difference here now is we're going to be using that compounding periodically formula, and if we're compounding once per year versus monthly or weekly or something like that, that's an n value of 1. So if I write this formula out, you have 1,200 times 1 plus 0.04 over 1 to the 1t. So both of these n's became 1. Now if we look at this, we can see that this formula, 1t is actually the same thing as just t. And if I simplified this addition, I would end up with the same thing that's over here. So I'm just going to write that out as a simplified version. So we have a basic formula, and this is in general the way life works. If we don't need something that's more difficult, we can take difficult concepts and oversimplify them or take out some details. So really, this formula here is just a really specific example of this formula where the n is 1. Now, when you were in Algebra 1, the basic formula is all you learned because you didn't have to think about the complicated details. But the idea is, and we're going to write it down here, the basic formula is a simplified version of the compounding periodically formula. Where there is n equals 1 compound per unit of time. So we really, at this point, could get rid of the basic formula, but it is nice, it's easy to use, and it's probably, in a lot of situations, along with PERT, P times e to the RT, the main one that we do end up using. So that leads to our next question, where does e come from? We have this, this number e that shows up in the middle of our problems, and all of a sudden, it's irrational. So we're going to see where that came from. So we have a really specific situation. It says James invests $1 in a bank account. So that means my p-value is $1. This is an extremely profitable account that grows 100% interest each year. So that's an increase, a positive r value, and we know the number 100%, if we write it as a number, is just the number 1. Okay, so the r value is not some sort of decimal here, it's actually 1. Now it says how much money will be in the account after 1 year. So t is also 1, or we're measuring in years, to the nearest thousandth with each compounding rate. So the n is the value that's going to vary throughout the problem. So when I say once per year, we're still going to write out the compounding periodically formula. We just talked about how when n is 1, we could use the basic formula, but here we're going to write it out with the compounding periodically. So we have p, let's write our formula since this is what we're focusing on. So we have p is 1. We have the 1 that's already in the formula, plus r over n. Here n is 1, 1 over 1 to the 1. Okay, so we're going to see what this is. If I think about simplifying this, this is actually 1 times 2 to the first. But I'm just going to type it in my calculator because we're going to get in that mode. And we do see that this does equal 2. So $2 with that method, which is exactly what we would expect, right? If I get 100%, I should have double what I had the previous year. Now we're going to look and see what happens when we type it in for monthly. So now in this problem, our n value is 12. So everything else about this problem is going to stay the same. One thing I should have, or wish I had written over here, the n and the t are 1, so that exponent is 1 times 1. It doesn't make a difference, but just realize there are two numbers there. So here, n is 12, so we're doing 12 times 1. So I'm just going to take a second to type that in the calculator, and hopefully you'll do the same. So if I type that in my calculator, I get that now I get $2.61 to the nearest cent. So the reason, if we think about it, is that we've talked about this before with that compounding periodically formula, that we start getting interest after the first month. And then when the next piece of interest builds in the second month, it's building off the stuff that's already there. So we actually end up getting more interest with that compounding versus waiting till the end of the year. The next one says daily. So let's see what happens when we compound daily. So for this one, how many compounds are in a year? There's 365 days in a year. So 1 times 1 plus 1 over 365 to the 365 times 1. So we're not getting a whole lot of interest. 1 over 365 is not even 1%, but we're getting it very often because it's happening every day. So if you're using your calculator, you can just replace the 12s with 365s. And that should give you $2.71. So the last one we're going to do on here is hourly. So there are actually 8,760 hours in a year. So we're going to be compounding tiny, tiny interest many, many times. And we'll see what this ends up being. Ignore that line right there. So replacing my 365s with 8,760. And this one, and we'll see, barely makes a difference. Even though I've compounded thousands more times, I get $2.72. So really, when we went from just one compound to 12 compounds, that had a bigger difference than going from 12 compounds to 8,760. And that's because as the compounds grow larger, our money doesn't keep growing forever. It's not like all of a sudden I'm going to have $100 if I just compound more frequently. It's approaching a famous number. So it says as the number of compounds grows larger, your answers are approaching a famous number. Do you know what this number is? So if you remember, and also from our question at the top, this number is E. So if you have a calculator, I'm going to write it out. This is the value of E. And this is an approximate value because it's irrational. But the numbers we can see on a calculator when I type in E, and if you are using a calculator, this number, I have to go all the way out to the 10,000th place to have it be different from the 2.718126691 I got from this answer. And so if we compounded 1,000,000 times, it would just get closer and closer to this irrational number. Remember, these, it looks kind of like there's a pattern here, but there isn't a pattern. There's just a lot of 1s, 8s, and 2s that we can see on this part that shows in our calculator. So the definition of E is defined as the limit as n approaches infinity. So this is a little bit of preview of limit notation for 1 plus 1 over n to the n. So this is saying as that n value gets bigger, I dropped this one because it doesn't matter. I dropped this one because it doesn't matter. But as we go towards infinity, that expression approaches the value of E. So you do not need to know the limit notation, but figured I'd write it out. Looking at the next page, this is our last one. It says, if something grows 5% per year, is that the same as growing 50% every 10 years? And this is a super common mistake people make. it kind of seems like, and even if you think about it, if you weren't in this unit, you probably would think, if I got 5% a year, that would give me 5 times 10, 50% in 10 years. But we're going to actually see what happens with an example. It says, we will start with 100 to make the problem easy to work with. If the investment grows 5% per year, what would be the final amount after 10 years? So that's a 1.05 to the 10th. And if I type that in my calculator, I would get that I have $162.89. So that's what we know is true from our basic exponential formula. Now, if the $100 did grow 50% in 10 years, how much would it have been? So I know 50% of 100 is $50. So if I grew $50, I should have just $150. But I had $162.89. So I actually got more than 50%. Now we're going to calculate what percent did I actually get after 10 years. So the way we can find percent change, the 50 was super easy to figure out because I picked 100, so it's easy to know 50% of 100 is $50. But now we're going to use our percent change formula, which is the amount something has changed over the original value times 100. So you've done percent increase and decrease before in math. I'm just pulling that formula up. Now, how much did my money change? My money changed by $62.89. So that's how much it increased. My money started at, the original amount I had was 100. And then to get a percent, this is going to give me some sort of, decimal, I'm going to multiply by 100. So because we're working with $100, everything becomes a lot easier to just know. I can see that this is going to equal 62.89%. So I didn't get 50% from 5% per year. I got 62.89%. Now, there is a way to actually figure this out. So our $100 made it almost kind of obvious. But what you need to do to convert between years, we can't just multiply, and we'll talk about why in a second. I have to take the 1 year base. So my 1 year base is the 1.05. And I don't multiply it because time is not multiplication with exponential growth. Time is in the exponent. So if I raise this to the 10th, that's going to give me the 10-year growth rate. So if I type that in my calculator, this shouldn't be a surprise. I get the decimal 1.6289 approximately, which goes along with, if I needed to read this decimal, if I was looking at that as a base, that's a 62.89% growth rate. Now this is such a common problem in the way we look at things. In general, whatever you want to talk about, psychology, biology, whatever it is, there's something that makes us think linearly about things, but it doesn't work for things exponentially, which is the way our world works in a lot of ways. Computer processing speed grows exponentially, money grows exponentially, stocks, prices, anything, with money, even populations can grow exponentially. Bacteria, we talk about growing exponentially. So it's important to remember that with exponential growth, no matter what formula we're working with, time is in the exponent. With exponential functions, you cannot think linearly about time. So when I talk about 10 years, I can't just multiply by 10. It's really that 10 is the exponent. And that's not even something that I can really know. I have to, type it, calculate it. Okay, so our intuition can sometimes be wrong about exponential functions. So to go along with this and to kind of close, here's a thought experiment. It says, if I asked you to go out your front door and take 30 steps, I'll bet you would guess about where you'd end up without even taking that short walk. So you could think, if I walk 30 steps, like I'm standing in a classroom, I would probably be out of the classroom. I could maybe make it down to the library. It's a simple linear step-by-step experience you've done 1,000 times. But what if I told you to take 30 exponential steps? As in, your first step is 1 step. Your second step doubles in size. So your second step is the size of 2 steps. 4 steps, 8, 16, 32, 64. So the question is, if you took 30 exponential steps out your front door, where do you think you'd end up? Now, if I heard this question, I would say, I don't know, maybe a mile down the road. Like, I know it's supposed to be big, right? I know what an exponential function looks like. But the answer is, and I calculated this to confirm it, 26 times around the world. Goes to show that we'd have trouble thinking exponentially.